Good.
Okay. So thank you for the invitation and also for the nice introduction. So today's talk is entitled Robust Anomaly Detection on the Circle, which is a joint work with Giovanni Borso from the University of Cassino. So let me go directly to the point. So here on the circle, we have that two observations seems to be far away from the majority of the data. If we use a standard method here on using the outlier index plot, where we have our data points and then the thresholds, we see that none of the points are declared as outlier. So we developed another procedure in order to detect outliers on the circle using robust methods. So I will actually start by discussing the outlier detection problem on the circle, then I will tackle the task of robust anomaly detection. After that, I will illustrate the proposed method through some real data examples, and I will conclude by giving some final remarks. So what is an outlier? An outlying observation is an observation that deviates from the fit of measure suggested by the majority of the observations. But when dealing with circular data, observations should be concentrated to a certain extent. For instance, if we have the data all over the circles, like within the case of the uniform distribution, it doesn't make sense to do outlier detection. So within the literature, several methods for outlier detection by dilation has been proposed. So for instance, Collett introduced some tests of discordancy, but those tests are suitable only for small sample sizes, and they are able to detect only the presence of one single outlier, while Rao and Sengupta also proposed the locally most powerful invariant statistic and the likelihood ratio, under the assumption that the concentration parameter is known. Actually, if we look to the C-stat proposed by Collett, which is based on the relative increase in the value of the sample mean resultant length, then we compute it and we get our threshold through simulations, we see that the 2 points which are candidates to be outliers are not detected. This is also obvious from moving to the outlier index plot. So the solid red line is our threshold, and then none of the points is declared as outlier. So actually this is due to a masking effects, because if we remove one of the points and then we compute the C-stat again and compute also the threshold, we see that this point, the red point, will be detected as outlier. This is also shown here within the outlier index plot. So the red solid line is the new threshold, and then this point exceeds the threshold, so it is flagged as outlier by this method. Okay, other outlier detection methods are available within the literature, but each of them has some limits. For instance, Abouzei et al. Proposed the circular distances, but those circular distances are suitable to detect only single outliers. So an alternative way to deal with the problem of outlier detection is to use robust statistical technique. Within this context, Agostinelli introduced the weighted likelihood and minimum dispersity methods, but also these methods have some limits, which are that their method depends on the choice of a bandwidth and of alpha parameter, and they didn't also give a rule to flag outliers. So a measure of robustness on the circle is the bias. We know that the bias of a function is bounded, so there is no possibility of comparison. This is why the standardized bias can be used in this case. So classical estimators of the location, we have let's say the classical estimator of the location is known to be the circular mean, which is also known to be non-robust standardized bias. As a robust estimator of the location, we have instead the circular median, which is given by this formula, which is also known that is the robust standardized bias. As for the dispersion, as a classical estimator, we have the famous maximum likelihood estimator, which is also known to be non-robust standardized bias, and as a robust estimator. Within the literature, we found the co-estimator, which is given by this formula. I will go back to these actually estimators later. And this estimator is also known to be robust standardized bias. So why actually we need robust statistics? So robust statistical methods aim to find the fitting for the majority of the data, which is similar to the fit without the outliers, under the assumption that the majority of the data that are supposed to be clean follows a specific probability distribution. And then we can actually use them in outlier detection to flag those observations that deviates from the robust fit. So our actually robust anomaly detection rule has 3 steps. So first, we assume that the majority of the data follow a specific probability distribution and then estimate its parameter in a robust way. And then we flag an observations as an outlier if the shortest arc distances from that point, the observed point with respect to the estimated mean is greater than the threshold C alpha of kappa hat. So the third step is also composed by 2 main steps. So I actually said that we flag an observation as an outlier if the shortest arc distance from that observed angle from the estimated mean exceeds the threshold. So here we compute the shortest arc distance of each observed angle, phi I from the estimated mu. So given this formula, and then we compare them with the cutoff value C alpha of kappa, while alpha is the expected proportion of points that are that will be flagged as an outlier while they are not. So actually, C alpha of kappa is given by 1 minus alpha divided by 2 quantile direction of the considered distribution. So here in this work, we assume that the majority of the data follow a specific probability distribution, which is the von Mises distribution, where its density function is given by this formula. Then within the second step, we use the Fisher circular median and the co-estimators to estimate the location and the dispersion of the distribution in a robust way. So actually, the co-estimator is given by phi minus 1 of the 0.25 quantile divided by the CMAD of C squared, where CMAD here is the circular median absolute deviation of the set C. Then within the third step, we flag an observation phi I as an outlier if this shortest arc distance between the observed angle and the median, estimated median, let's say exceed the threshold. So the first example is about, to illustrate in a way our method is about the Northed Creek frog data, which involved the direction of 14 Northed Creek frog where their homing ability was recorded. So here what we do is we compute the median and also the co-estimator and our cutoff value. So here actually what we did also is to compute the maximum likelihood estimator, estimators for the location and dispersion. So here we see that the maximum likelihood estimator for the concentrations decreases from let's say is 2.17 while using the co-estimators is 2.70. So then we compare our proposed method with the C-stat discussed earlier. So here on the circle, we see that this outlying observation is detected by our method, and it's also detected by the C-stat. So actually, this plot is a circular outlier map, where within the x-axis we have the angles in radians, and on the y-axis we have the distances in radians. Then the solid red line is our cutoff value using our robust procedure, and then the points which are within the circles are those points that are flagged as outliers using the C-stat. So within this example, both methods works well. In a way, our robust methods is able to detect the outlier and also the standard method. Then the second example is about the walking direction of 32 long-legged desert ants. So here we have that. Using our robust outlier detection methods, we have 3 data points that are detected as outlier. Meanwhile, using the C-stat, we have only 1 point which is detected as an outlier, and this is because the C-stats works only with single outliers. The third example is the example that I presented earlier. So here we consider a sample of 22 resultant direction moved by 22 Sardinian sea stars over a period of 11 days after displacement from their natural habitat. So what we did is we computed again our median and co-estimator and our cutoff value, and then we used our, let's say, rule in order to flag the outliers. So here directly from the circular outlier map, which is a graphical useful tool that can directly give an idea about the presence of outliers, shows that 2 points exceed the threshold. So these 2 points are outliers. Then the last example is about the Drosophila fly larva data, which represent the 180 change in movement of motion of a Drosophila fly larva measured once per second over a period of 3 minutes. So actually I give these examples just to show you that first, using the C-stat, only one single outlier can be detected, and then even using let's say, a robust method, we can have some problems. In a way, the circular outlier plot is not only useful to see the outliers, but also to question the assumption about the distribution, because for this data, it's known within the literature of directional statistics that is a bivariate. So in a way, this actually the assumption about the distribution may be not adequate for this kind of data. So to summarize, actually, I presented an anomaly detection procedure based on robust estimators on the circle, and I also introduced an outlier plot for circular data. Then, as future works, we intend to develop alternative robust estimator of the concentration parameter kappa, and also to extend the anomaly detection rule to other circular distribution, for instance, for the rapid Cauchy, and finally to extend the procedure to find outliers in circular regression. So here I leave you a list of the main references used in this work, and thank you for your attention.